In this work, we start by going to the model wizard. Under the select space dimension, select 2D axisymmetric. We select heat transfer, then we move to electromagnetic heating, and you add the induction heating. The next thing is to go to the steady, and you select frequency transient. Then you click on done. Okay. So now that we are here, we can quickly start by adding our parameters. So we're going to input our parameters manually. The first will be I0. To E3. Okay, so I'm going to skip this part. I'm going to pause and skip this part so that we can. Okay, now let's continue. Let me do it. As a unit in amperes. So this is the current. One is the reference temperature. It's 293 Kelvin. Yes, T naught. R naught is resistance at T 1.75 for exponent -8. Unit is ohms meter. Resistivity at T equals T naught. Put under value A1 as 0.039 per Kelvin. As the temperature coefficient. Next is to add the cooling channel. Radius with 5 mm. Next is the cooling channel X section. You see, we're going to use all these parameters in the work. That's why we have to input everything in here. See. is a cooling channel X section. And put the value empty for the mass flow. One is 1 kg, 10 minutes. Cooling water mass flow rate. Last will be the cooling water inlet temperature, which will be reduced 10 degrees Celsius. Okay. So you should input all these parameters manually like this, then you can move on next to building our geometry. Geometry, we add a triangle, rectangle, so locate the size and shape. The width will be 0.2. The height will be 0.5. Under the position, you locate the C field and it will be minus 0.25. I think we can build this. We add another rectangle. This will have a width of 0.03 and a height of 0.1. So this, the position will be at minus 0.05. We also build this. Next, we'll add a circle. Radius of 0.01. Position where we have the arrow field will be 0.05. Also build this selection as well. We add another circle. Size and shape, radius. We put in RC. Go selected. Should be same as this radius of RC. And the base should be 0.05. 0.05. Okay. Now click on form union. We'll build a, you go to add material. Let's add material from library. What we'll be adding is a circuit board. So you go to built-in, look for this, you add. Also, look for AC/DC, add a copper. Also, select water. You have to add water. So now we've added circuit board, copper, water. Now let's go to the copper. And copper will be at domains 2 and 3. And you expand this copper, you go to the linearized resistivity. Under the properties, let's locate the under output properties. We're gonna make some changes here. So here, this will be R naught. This will be A1. And this will be T naught. Let's go to water. Let me put to be at domain 4 only. So this water does not provide the values for let's close the section. Our relative permeability and relative permittivity. So we put in the values there. The value will be A0. And permittivity will be 1. Also, for the thermal conductivity, we want to increase the thermal conductivity of the water to model the efficient heat transport in turbulent flow. So in here, this value then changes to 1 exponent e exponent 3. Let's go to magnetic field. So we're done now with the parameters, the building the geometry, adding the materials. Now, next is to do the physics and study. Okay, so For the Ampere's law, we add another one Ampere's law too, and that will be for domain 2 and 3 only. So we locate the constitutive relation DE and also that for the JCE. From this conduction model, let's use a linearized resistivity. Domains, we select coil, and it will be for domain 3 only. Let's locate the coil section. Under the coil currents, put in I naught. We go to heat transfer in solids. So now we're done with the magnetic fields. Now we want to look at the heat transfer aspects. We select the temperature, boundaries 2, 7, and 9. And these temperature sections, we put in our value for T naught. For our heat source, let's add where the heat source will be. Will be from domain 4. Locate where the heat source will be. And for this general heat source, we have to put our own expression here. MT times HT dot CP times N minus T have 2 times pi times R times AC. So you put this expression in here. So now that we are done with this video, we go to mesh and we just build all. We have something like this. Now we can move on to study this work. So let's go on to our study. Let's go to frequency transient. Let's locate the steady settings. Time list. Let's use H and select the range. Step field, let's put 10 minutes. And under the stop, let's put 10 hours. We'll replace. So we locate the frequency. Right, and we put 500 Hertz. Now we can compute this work. Take some time to finish computing. So we have the revolution plots. Okay, let's go. We have some plots here. Temperature 3D plots. See the revolution plot of the 10 hours. This shows, so let me see. This shows the revolution plot after 10 hours in here. Temperature distribution after 10 hours. Let's do a cut point 2D. So where we have our point data section, here will be 0, here will be 0. Let's duplicate this. Here will be 0.05. Let's put a 1D plot group. Let's see if we have 1D plot group. Click. I want to do a point graph. So as you can see, you have several plots, magnetic flux density as well, and all that. Let's go back to what we're doing. We want to right click this and you add a point graph. And under the data, you select the cut point 2D one. This expression here, we're going to replace it. Let's go to heat transfer. Let's go to temperature. Let's use temperature here. We're going to duplicate this. Duplicate. And under the data section, we use cut point 2. Now we plot. So the plot shows the temperature evolution in the center of the copper cylinder and the cooling channel. We compare this and that. Point 1, this plot, that plot. No, you should have something like this. And this the plots that you can get at the end of this work. So if you have any questions with this, and I think this is quite straightforward, let me know. So I'll see you in the next video and thank you for watching.